Okay guys, this is our second problem on ideal Rankine cycle. We are studying a steam power plant that operates on a simple ideal Rankine cycle. So this is what we have studied. We are being told that the net power is 45 megawatts and operates between 7 megapascal and 10 kilopascal. The entrance temperature is 500 degrees, and we are cooling the condenser with 2000 kilograms per second of water. So we are asked to get the thermal efficiency of the cycle, the mass flow rate of the steam, and the temperature rise of the cooling water. So similar to what we did in the last video, we are starting with our diagram, trying to put as much information as we can. We draw the pump, the boiler. Now we're doing the turbine, indicating the power input of the pump, the heat rate input, the power output of the turbine, and then finally the condenser. And in the condenser, what we are doing now is we are just doing a small cartoon of what is going on inside. We have in black the steam tubes, and in blue we have the cooling water tubes, and this is where we know that we have 2000 kilograms per second of water, and we are indicating here in red that this Q out, the heat that we are rejecting in the condenser, is the same heat that is going to be absorbed. Is going to be absorbed by the cooling water. So we are now drawing our TS diagram that we are also required to do. And first of all, we draw our dome. Remember, this is not exact, so it's just a representation of what is going on. We start by drawing the lines of constant pressure. This is our condenser pressure, 10 kilopascal, and this is our boiler pressure, 7 megapascal. And then we know that we have our pump going from 1 to 2, connecting both lines, and then the turbine will draw a vertical line since it's an isentropic, so it's 3 to 4. Now that we have our drawing, we just complete it with the 500 degrees temperature that we are indicated for the entrance of the turbine. It makes it superheated vapor. And finally, we are going to just clearly state what we were looking for, what we are asked to find. First of all is the efficiency of the cycle. Secondly will be the mass flow rate of steam. Please don't get confused, because the 2000 kilograms per second is the mass flow rate of the cooling water. And finally, the delta T, the temperature rise of that same cooling water. Okay, so we have two mass flow rates, cooling water and steam. So before we start looking for numbers, what we are going to do is solve the equations, and then at the end we are going to find out properties and just substitute. Okay, so this part is what it's really solving the problem. So we're going to start by the more general part, and we start by saying that efficiency is the net work divided by the heat in. You can notice that we are not using power, we're using specific work, specific heat. And the reason for that is that since both are affected by mass will be cancelled both. Okay, so we are we know that the net work is the difference between the work of the turbine that we are getting and the work of the pump that we need to provide. So that's the net power that we are left to generate electricity. And the work of the pump should be pressure 2 minus pressure 1. Since we don't have compressed liquid tables, we are going to use this approximation. And for the heat input, we just have the enthalpy difference between the outlet of the condenser H3 and the outlet of the boiler state 3 and the inlet of such boiler state 2. In order to get the mass flow rate, we know that this power plant delivers net power of 1750. So that is equal to the mass flow rate of 45 megawatts. So that's the mass flow rate times the net work. So just solving for ms, we will get the mass flow rate of steam. Remember that this is different from the 2000 kilograms per second. And finally, what we do in the condenser is an energy balance. We know that this condenser power that we are dissipating is equal to the mass flow rate of steam. That's the steam that is circulating inside the Rankine cycle, and should be exactly the same as the amount of heat that we are returning with the circulating water. That is mass flow rate of cooling water times the CP, the specific heat constant pressure for water, and delta T. So solving for the temperature rise, we know that is the mass flow rate times the enthalpy difference. This is the heat rejected by the condenser, and it's divided by the mass flow rate of cooling water times the CP of this cooling water. And as we mentioned, CP is 4.186 kilojoules per kilogram Kelvin. With this, we already solved our problem. What it's only needed is to gather the properties at each state. So that's what we are going to do next. So, as we mentioned, we need to find out the properties. So we start with state 1, which since it's an ideal cycle, we know that its quality is 1, and the pressure is the pressure in the condenser, which is 10 kilopascal. So we look in our table 5. We use table 5, that is saturated vapor, and the entrance is pressure. So we notice that all of this data is what we're going to do, specific volume, the enthalpy, and the entropy mainly. So copying that information from the table, we know that H1 is 191.81 kilojoules per kilogram, while volume 1 is 0.001010 cubic meters per kilogram. And that defines state 1. State 2, we remember that we have an isentropic pump. We don't have compressed liquid table, so we use this expression. It's just the first law for that pump, and since we don't know the work of the pump, we can estimate it doing the specific volume times the pressure difference. In theory, it doesn't matter which specific volume we choose. since it's incompressible. That means that the density will be the same. That means that the specific volume will be the same long, and that's the approximation. This 7.06 is the work of the pump. So when we get to the point of needing to find a network, this will be the work pump that we need to subtract from the turbine work. The total is 197.88, so this is, and actually this is a mistake, should be 198. Okay, along the problem we'll have an error of 1. Please make sure that you correct that. I am not gonna repeat this video. Okay, so now we go to state 3, which we know is superheated vapor, and we need to go to our table A6. We move and we see that in table A6 for superheated vapor we have two entrances, pressure and temperature. So we know our pressure is 7 megapascal and 500, and it's indicated here. Our enthalpy is 3411.4. 6.8 is the entropy that we're going to use. So that will define our state 3. We just write the numbers that we have. I'm doing this in order to copy them. You will have the advantage of having in front of you. And as we saw in class, this could be much easier with ease, but we need to learn to do it by hand so we understand what is doing. We don't forget to put the units on each of them. Kilojoules per kilogram Kelvin. State 4, we need two properties. We know one is the pressure. Pressure is 10 kilopascal. We need a second property, and we recall this is an isentropic pump. So entropy 3 will be equal to entropy 4, which is 6.8. Now, how do we know which kind of what the state, or where is this state 4? We need to compare S4 with the saturated vapor at 10 kilopascal, the entropy of saturated vapor. If the value that we have for saturated vapor is bigger, that means that we have a mixture. If the value of S4 is bigger, that means that we have superheated. And if it's exactly the same, it is saturated vapor. So SG is 8.14 versus 6.8. We know that we have a mixture, and we know that we cannot use temperature because they are not independent. So we are computing the quality. We use the values that we have. 6.8 is the value for entropy for state 4, and we subtract SF, that is the entropy at saturated liquid at 10 kilopascal, and we divide it by SFG, which is the difference between saturated vapor and saturated liquid. Is the entropy of vaporization, and this value will give us the quality. We have a quality of 0.82. That means that 82% of the mass that we have is in vapor phase. The remaining 18% is in liquid phase. So with this, we have finished computing our properties. We are using the value of quality that we computed, and to find out the enthalpy at the end of the exit of the turbine, which will be the entrance of the condenser. So the quality that we compute with entropy is the same quality we will use with specific volume, the same quality that we use with enthalpy and with internal energy. Quality is adimensional. So next we are going to use all this data that we computed, that we generate, in order to substitute into our expressions and find out the work turbine. I think this is pretty clear, so not much of a talking for me. I'm just indicating the operations and writing the final number. You are not only encouraged, but you are required to check these numbers. You already see that I committed a mistake of 1. So we are computing the network, and here's where my mistake is. Instead of 1, oh no, it's on the it will be on the hit in. Lucky us, this is a big number, so difference on 1 will not be of great impact. Is 1 over more than 3,000. So we can compute the power, the mass flow rate. We have our 45 megawatts. We need to convert them to kilojoules per second or kilowatts in order to cancel the units, because the units are in kilojoules per kilogram. So we cancel kilojoules, and at the end we have kilograms per second. And remember, this is the mass flow rate of steam. It's not the cooling water, it's the steam that circulates along the turbine, the pump, the both heat exchangers. 35.98 kilograms per second, and we mark it since important and required data that we are obtaining. Now we can compute Q in, which is what we need to find out efficiency, and this Q in will be just H3 minus H2. Remember that it's H2 where I have a mistake, so you need to correct that. That will barely affect our number. And efficiency is obviously the net work divided by the heat supplied. I hope this is clear for you guys. And efficiency, we find it to be 38%, 0.38, 84. If we multiply times 100, we will have it in percentage, so that will be 38.84%. Okay, that's our second result, and last but not least, we are looking to find a temperature rise in the cooling water. So we just substitute the numbers that we got in our analysis. So this is Q out divided by the Cp of the water, and we use water because it's a cooling fluid. If instead of water we have air, we should use Cp of air times the mass flow of the cooling water. So Q out, we find it by multiplying the mass flow rate, which is 35.98 times the enthalpy difference. This number comes from subtracting H4 minus H1. that we are indicating right now. 191.81, and we divide this by the product of CP, which we already stated is 4.186 times 2000, and this temperature rise is 8.4. So as you can see, solving each of these is applying first law analysis to each component, and the next video we're going to describe some ways to improve the efficiency of the Rankine cycle, and we are going to talk about the difference between the real cycle and the ideal one. Okay, thank you guys.